Hello physics fans and welcome to my lesson on work and power. This is Mrs. Jones. This is topic 8 if you are doing triple science and topic 7 if you are doing combined science. This is actually the whole topic. I'm not quite sure why that is, but let's get started. So the first thing we would normally do is to have a think about what the words work and power actually mean, because in physics they've got very specific definitions compared to what you would normally use them for in real life. And also maybe think about having a go at the units for some of these quantities that we'll be talking about during today's lesson. The first very important thing to note about work or work done is that it is an energy quantity. So the unit for work done is actually joules. The same as for gravitational potential energy and kinetic energy, it's measured in joules because it's an energy quantity. People often forget that work done is energy because it's the only one that doesn't have energy in the title, like kinetic energy, for example. So it's defined as the energy transferred by a force. So if a force is used to move an object, we can calculate the work done. The power is related to work done, and we talk about it in the same lesson because the power is the rate of energy transfer. So the amount of energy in joules transferred per second of time. So anything divided by time is a rate or the speed at which something's happening. So with power, it's how quickly is the energy being transferred by any particular object or device. Down here we've got the link between watts and joules per second. So 1 watt of power is equal to 1 joule of energy transferred per every second of time. So we'll be able to look at how we're going to calculate these during the lesson, and also how these two can be linked together in questions. So during this lesson we're going to have a look at how we can work out work done and power. We're going to have a look at the equations and have a look at linking the equations together, so we can answer questions where both of these equations might be required, because I've seen that pop up a couple of times on past exam papers. Also, we're going to recap something we did in topic 3, which was looking at energy transfers, because even though it's a paper 1 topic, I have seen it pop up in paper 2 on numerous occasions. So it's important that we can identify the energy transfers in a system as well as being able to do the calculations. So here's the equation for calculating work done. As you can see, work done is measured in joules, as are the other energy quantities, force in newtons, and of course distance measured in meters. So if you get any distances given in kilometers, you need to convert that to meters. If you get any work done values given in kilojoules or megajoules, for example, they need to be converted back into joules before you can process them in the equation. This is one of the equations that you have to remember. It's one that you need to memorize. Some of the equations are given on the back of the paper, but this isn't one of them, so it's one of the ones that you've got to go into the exam already knowing in your head. The other option is to memorize the triangle instead. In the triangle, the capital E is for work done, stands for energy, and then of course force and distance. Sometimes you see distance being represented as a lowercase x, but in this case it's represented with a lowercase d. The other thing to note is if you get a question where an object is being lifted upwards against its weight, then the weight becomes the force that you need to apply to actually lift it. So just in case you get a question calculating work done where you're using the object's weight and it's being lifted upwards, you can use the weight in place of the force. Okay, so here are a few questions using the work done equation. What you can do if you've not already done these questions is you can pause the video and have a go at the questions and then have a look at the answers afterwards to see how you did and compare them to what I do on here. So for the first one, it's asking to calculate the amount of work that's been done by the cyclist. The first thing you want to do is check if any conversions need doing, which they don't in this case because we've got 250 metres and 1000 newtons of force. So for this one, we can simply just calculate it by doing the force times the distance. So for the first one, it's just using the equation straight as it is, and the answer for that is 250,000 joules, or if you want to put it into kilojoules, it's 250 kilojoules. Keep an eye out for the unit that the exam question wants you to calculate your answer in. Sometimes they'll ask you to give the unit, and sometimes they will ask you to calculate it in joules or kilojoules, so just keep an eye out for what they are actually asking for. If they're asking you to state the unit, then there'll be a mark available for it as well, so just have a look out for that and make sure you don't leave any of those unit lines blank. For question 2 and 3, the answers are on here, but I'm going to go through the answers to those in a little bit more detail and how you calculate them on the next couple of slides. So for question 2, the answer is 50 metres. For question 3, it's 200,000 newtons. So if you got that, you can just skip the next little part of the video where I go through explaining these and how to calculate them in a little bit more detail. In question 2, we have got a conversion to do before we actually process the numbers in the equation. If you look here, we've got 10,000 newtons, which is fine, but we've got 500 kilojoules here of work done. So the first step is always to check what numbers you've got and see if you need to do any conversions. There tend to be quite a few marks available for this on higher paper and a couple of marks available on foundation paper for doing this, so it's always good to do. So first thing to do is to convert the kilojoules to joules. If you want to do that, you've got to remember that a kilojoule is 1000 joules. So with any kilojoule value, you've got to times it by 1000 to get the joules value. So we've got 500,000 joules here is the same as 500 kilojoules. That's the first step. Then what we need to do is have a look at the triangle or have a look at the equation to see what we need to do. So we've got the force and we've got the work done, and we need to calculate how far the cars travel. So we are calculating the distance here. So to do that, if you look at the triangle, you've got to divide the work done by the force that's been given to give you the distance. So that's 500,000 joules divided by 10,000 newtons, and that will give us the answer of 50 metres. It's always really good when you do a calculation to sense check your answer. So does that answer make sense? Well, it's a car that's moving along, and 50 metres seems to be a sensible distance for the car to have travelled. So always good to have a look at your answer and see, does it actually make sense in the context of the question? And this one does. So now we can move on to the next one, which was question 3. So in question 3, we've got a crane, it's our context, and it's lifting a load 20 metres upwards. And the work that has been done here is 4 megajoules. So the capital M stands for mega, and I always remember it as mega is million. So again, the first thing we need to do here is do our conversion from megajoules to joules. So to do that, we need to times our megajoule value by 1,000,000 to give us our joules value. So 4 megajoules is 4,000 joules. So that's the first step done. Again, there will be a mark available for the conversion. So if you don't do the conversions, you won't lose all the marks, but you will lose one. So if there's a few throughout the paper, then you could end up dropping 2 or 3, maybe even more than that marks during the paper. So it's worth looking for. The next job is to either have a look at the triangle or have a look at the equation. So if we look at the triangle, it tells us we need to do the work done divided by the distance given here. So that's 4 million joules divided by 20 metres, and that gives us an answer of 200,000 newtons, or if you put it in kilonewtons, it's 200 kilonewtons. The other way of doing it is to write down the equation as you've learnt it. So work done is force times distance, and then substitute the numbers that you've got into the equation. So the work done in the question is the 4 million joules. So instead of writing E, we substitute that with the number. And then the force is what we're trying to work out, so we can't put a number in for that yet. And the distance is 20, so we replace the distance in the equation with the actual distance given in the question, which was 20 metres. And then when you've got to this stage, you've substituted, the next thing to do is to perform the opposite operations to get force on its own, because we want to find out what force is. So we think about what's happening with force on this side of the equation, and it's being times by 20. So the opposite of timesing by 20 is to divide by 20. So if you do that to both sides of the equation, it cancels out the 20 on this side, and then we can work out what force is by doing the 4 million joules divided by the 20 metres, which again gives us the 200,000 newtons. So it's the same answer, just a different way of getting there. So I also asked you to have a think about the energy changes that might be happening in each of these situations. And they're all quite similar actually. For the first one, we have got the cyclist cycling along on the bike. So the energy stored to start with here is the chemical energy store that is stored within the cyclist body. And when the cyclist pedals the bike, that chemical energy store is transferred mechanically or by forces, the forces of the cyclist's muscles, and that's converted into a kinetic energy store as the person and the bike start to move along. That's really similar to the next one, except the chemical energy is stored in the fuel of the car rather than in the body of the person. Also transferred mechanically. When the engine runs, the engine causes a force to be applied to the car and causes it to move. So the chemical energy store gets transferred into a kinetic energy store of the moving car. We know that we can calculate kinetic energy for an object by using the object's mass and the object's speed from when we looked at this in topic 3. We were calculating kinetic energy and gravitational potential energy in some cases. So it's important to know that the energy stores here are getting shifted, very, very similar for these two. And the crane also starts off very similar because we've got the chemical store in the crane's fuel transferred by forces or transferred mechanically to a kinetic store when the load is moving upwards. But then once the load has been moved upwards into the air, we have a store of gravitational potential energy. And if you remember back again from topic 3, we can calculate the gravitational potential energy using an object's mass, an object's height, or the object's change in height, and also the gravitational field strength on Earth, which is 10 newtons per kilogram, something else that you need to remember as well. The other thing to say about this is quite a common question is thinking about these ones in reverse, where you've got a vehicle or a bike or something that's moving and it comes to a stop. So for example, a car might brake and come to a stop, and it asks you to say what the energy changes are or the energy transfers are. So in that case, we're looking at a kinetic store of energy, then gets converted into a thermal store of energy, where the thermal energy when the car brakes is dissipated into the surroundings, or it heats up the brakes and the different bits of the car. So the kinetic energy that was in the moving car is then converted into a thermal energy store either in the car or in the surroundings. And that's quite a common question that I've seen come up a couple of times. Okay, here's a few more questions using the work done equation. We're going to give our answers here to two significant figures, mainly because when the exam board produce their mark schemes, they usually give their answers to two significant figures. And sometimes they ask for it in the question. So if they do ask for it in the question, there will be a mark available for it. So it's important that you're able to do that, because especially in the most recent papers, it seems to have been a thing that the exam board have been doing. So for this first question, we've got Josh pushing a book along a table at 5.2 metres and exerting a force of 5 newtons. So calculate the amount of work he does. So the first thing you want to do is recall the equation. So you will get a mark for recalling the equation if it's not given. So this is work done is equal to force times distance again. And then the best thing to do is to substitute the numbers in that you've got. So in this case, we have got the force and we have got the distance, so we can just substitute them into the equation and then perform the operation. and see what answer we get. So the answer to this is 26 joules, and that's already two significant figures, so that one we don't really need to do anything with. For the second one, we have got an amount of work that's been done pushing a wheelbarrow, and we've also been given the force, and we need to calculate how far it's been pushed. So here we're calculating the distance. So if we go through the same process again, we recall the equation and substitute the numbers in. So the work done replaces the E, which stands for work done, 247 here. The force in the question is 52 newtons, so we can substitute that into the equation. Instead of the F, we put the 52 newtons in and then times that by D for distance, which we don't know yet because that's the one we're trying to work out. So when you get to this stage, you want to find out what D is, you want to get it on its own and perform whatever the opposite operation is to get it on its own. So here it's being times by 52, so if we then divide that by 52, it cancels out the 52 here, but whatever we do to this side, we also have to do to the other side. So if we divide this side by 52, then we also have to divide the other side by 52. So D should be equal to 247 divided by 52, which then gives us an answer of 4.75. But we do want to put our answer to two significant figures. So we have a look. 4 is our first significant figure, 7 is our second significant figure. And if we have a look at the next number along, if it's 5 or more, we need to round that up by 1. So because this is a 5, we round the 7 up to an 8 and we end up with 4.8 metres, which is our answer to two significant figures. If we have a look at question 3, we've got somebody driving a car 1.7 kilometres. So I would stop there and I would make sure that I've converted this to metres first before I go any further. So the first step I would always do is to do any conversions. So if we times that by 1,000, we get 1,700 metres is 1.7 kilometres because kilo is 1,000. Then we need to have a look at what else we've got. We've been given a driving force here of 2,653 newtons. How much work did the car do? So we can use the equation just as it is, that work done is equal to force times distance, and substitute our numbers in, making sure that we substitute in our metres value this time and not the kilometres value. So we've got our force times our distance, and then if we perform the operation in our calculator, we end up with 4,510,100. So this here is not given to two significant figures, so we need to adjust that. So 4 is our first significant figure, 5 is our second significant figure, and then we just check the next one along to see if it's 5 or more. Now because it's not 5 or more, it's 1, we leave that 5 as it is and then just have the rest of the numbers as zeros, making sure that when you turn that to a 0, you've got the correct numbers of zeros here. So it ends up as 4,500,000 joules, and that is correct to two significant figures, or you could leave it as megajoules, and that will be 4.5 megajoules, making sure that your mega is a capital M and not a lowercase m. So, as mentioned before, power is the rate at which energy is being transferred, and it depends on two things. It depends on, first of all, how much energy is being transferred, or of course how much work is being done, and also the time it takes to actually transfer that energy. So if you've got more energy being transferred in a shorter amount of time, then the power is going to be greater. So given this information, you can actually work out the equation for power without me actually telling it to you. So pause the video, have a think, and see if you can work out what the equation is going to be before the next slide. Did you get it? Here's the answer, that power is equal to the work done or the energy transferred divided by the time taken. So power measured in watts, work done of course measured in joules, and time needs to be in seconds. So again, there's an opportunity here for the exam board to give you something to convert. So maybe it'll give you a time in minutes or hours, and you have to make sure that you convert that to seconds before you process the equation. Same with joules and watts. They might give you kilowatts, they might give you kilojoules or megajoules. So just again, watch out for those conversions. The sad news is this is another equation that you need to memorise. It won't be given on the back of the paper, so you've got to remember this equation when you go into the exam. And here's a triangle that you can alternatively memorise a triangle, as long as, of course, you remember what all the letters mean. So here we've got E, again, is for work done, as it was previously, capital P for power, and lowercase t is representing time. So just a bit more information here that we've already sort of talked about, that 1 watt of power is equal to 1 joule of work done or energy transferred every second. Work done and energy transferred are equal to each other, it's the same thing, and just remembering that power is a rate is sometimes going to be useful if you're asked to describe what power is in words, which again, sometimes you get questions where you have to describe an equation in words or explain the units for an equation. So it's always useful to remember that power is a rate. Here are some practice questions using the power equation. What you can do is, again, pause the PowerPoint, have a go at these questions, and then you can unpause and have a look and see what answers you've got and compare them to what we've got here. So for the first question, it's saying that Shane is doing 21 joules of work in 5.3 seconds. Calculate his power rating. So to do that, first thing we need to do is recall the equation for power. So power is work done or energy divided by time taken. Then we want to substitute. So we want to substitute in the work for the energy here. So 21 divided by the time, which is 5.3, and then perform the operation, and 21 divided by 5.3 is 3.9622, and so on and so on. On the calculator, it's a long number. Don't be scared of these numbers with lots of decimal places. Quite often the answer to a physics calculation will be something like this. We want our answer to 2 significant figures. So 3 is our first significant figure, 9 is our second significant figure, and then we check the next number along. So 6 we've got here is 5 or more, so we need to round this up, but we can't round up 9, so what we have to do is round the whole thing up to 4.0. So 4.0 watts is the correct answer for this to 2 significant figures. If they do ask you for significant figures and you don't give it, then you will lose a mark, so it's always, like I said before, worth looking for that. Here we've got Danielle running up some stairs, and she has a power rating of 569 watts. It takes her 20 seconds. Calculate how much work she did. So because we've got a time and we've got a power here, we still need to use the power equation, even though it's asking you to calculate how much work she did. So we recall the power equation and then substitute what we've got. So we can substitute in the 569 watts for the power. E is the work done, and we don't know that yet. Divide that by the time, which was 20. So here we need to rearrange the equation again, and what we want to do is get E, or work done, on its own, and E is being divided by 20. So the opposite operation to divided by 20 is to times by 20. So if we times both sides by 20, it cancels this 20 out and leaves E on its own. And if we times 569 by 20, that will give us our work done value, which is 11,380. We need to put that to 2 significant figures. So 1 here is our first significant figure, and the second one is our second significant figure, and then we want to have the rest as zeros. If we check the next number is 3. So because it's not 5 or more, we just leave it as 11,000, making sure that we get the correct number of zeros on the end there. So it's 11,000 joules, correct to 2 significant figures, or 11 kilojoules. With question 3, you've got a few bits of information here. You've got a force, you've got a distance, and you've also got a power rating of 60 kilowatts. So there's quite a bit to do here. I would always recommend, first of all, doing any conversions first. So the absolute first step here has got to be converting the 60 kilowatts into watts. So if we times that by 1,000, we get 60,000 watts. So that's sorted first. Then what we need to do is have a look what we have. We've got a force, we've got a power, and we've got a distance. So for this particular question, we need to use both the work done equation and the power equation. So first thing to do is to write down both of those equations, then substitute the numbers from the questions into the equation to see what you've got. So for the work done equation, we've got the force, which is 3,000 newtons, and we've got the distance, which is 113 newtons. So we can work out the work done using the work done equation, which gives us 339,000 joules. We can then substitute that into our power equation. So with the power equation, we've got the power, which was 60,000 watts, so we can substitute that in for power. We've used the first equation to calculate the work done, so we can substitute that in for work done and then divide that by time. That's what we're trying to work out here, calculate how long the journey took, so that's the missing value. But we need to use both equations to be able to work that out. So especially in the higher paper, you might get questions where you have to use two different equations. It might be worth 4 marks, so that might give you a clue whether you have to use two equations for some of these questions. So once we've finally substituted everything in, we need to try and get T on its own. Now, you can either do this in one step or two. If we want to get T on its own, we want to perform the opposite operation. So the first option, which is the long way round, is to times both sides by T and then divide both sides by 60,000. But what I always tell my students is that if something's on the bottom of an equation, you can take the thing that's on the top and put it onto the top of the other thing. It's the quicker way of doing it. So T is going to be equal to 339,000 divided by 60,000, which when we process that in the calculator, it gives us 5.65. And if we round that to two significant figures, our 5 here is 5 or more, so we need to round our 6 up to a 7. So our final answer is 5.7 seconds, correct two significant figures. I've included this experiment method for you to have a look through because quite often in the exam board want you to describe a method for an experiment or how you would take measurements or what measurements you might need to take to calculate the power of something or the work done for an object. So it might be worth just pausing the video and having a look through this method to see how this experiment would be carried out, just so you're familiar with it. The question at the side here is asking about why you are timing how long it takes for 20 lifts rather than just one lift. And if you increase the amount of time you are measuring, it makes the time that you're measuring more what they call measurable. So it means that the time you are measuring for 20 lifts is going to be more accurate than it would be for one lift, because you've got the human reaction times when you're pressing start and stop on the stop clock. And because it's a very short time, it makes it more difficult to measure. So if you increase the amount of time that you are measuring over, it increases the accuracy of your overall time. This does, however, cause an error when you're calculating power, because it includes the time it takes for the person to put the weight back down on the floor and then lift it again. So you're increasing the amount of time that you're measuring, meaning that the power value would be a lot lower than it actually should be, because you're including time that's not actually included in actually lifting the masses. So if you get questions about why a method might not be particularly accurate or how you could improve a method, quite often if it's a time that you're measuring, if you increase the amount of time that you are measuring over, it will increase the accuracy of your time measurements. Okay, so here's another question that uses both the power and the work done equation. So again, you can pause the video, have a go at this and see if you can work out the force needed to lift this suitcase. And I want you to give your answer to two significant figures. So have a look at the information and have a go. Alright, so the first thing we need to do is have a look at what information we've got. So we've got a power we have a distance, and we also have a time. And we want to calculate the force needed to lift the suitcase. So we do need to use both the power and the work done equations to do this. So the first step for this one is to have a look at the power equation and use it to calculate the work done, because we've got the power and we've also got the time, so we can calculate the work done. So substitute into the equation, we've got 103 watts of power instead of writing the word power, and we've got 0.7 seconds for the time taken. So then we can perform the opposite operation. The opposite of dividing by 0.7 is to times by 0.7. So if we do that, our work done is 103 times 0.7, which gives us 72.1 joules, and this is for our work done. We can then take this work done that we've calculated and put it into the work done equation. So that is work done is force times distance. We've got the work done calculated here that we can substitute, and we also have the distance, which was 0.26 meters, that we can substitute in. So if we do that, we've got 72.1 is equal to force times 0.62 meters, and the opposite of timesing by 0.62 is to divide both sides of the equation by 0.62, and if we do that, we end up with 72.1 joules divided by 0.62 meters, and that gives us 116.29 and lots of decimal places on the calculator when you punch that in. And we want to convert that to two decimal places, so not two decimal places, two significant figures. So here we've got the first one is our first significant figure, and the second one is our second significant figure. Because the next number along is 5 or more, then we need to round this one up here to a 2. So what we end up with is 120 newtons. We don't need to carry on with all these zeros past the decimal place. So as long as we've got the correct number of zeros in the hundreds here, then our answer is correct to two significant figures. So that gives us 120 newtons. Okay, so lastly, we've got a bit of a wordy question here, and sometimes you get these. So it's saying that we've got two people with the same mass, how convenient, running up a hill, and the first person takes twice as long as the second person. So compare the work done and the power of the two people. So how is it similar and how is it different? So first of all, if we compare the work done, we've got the same force and distance because of the same mass, same weight, and they're going either going the same distance. So the amount of work done, the force times distance, will be the same, because if we times those two together, we'll get the same number. So they've got the same mass and they're going the same distance. In terms of the power, because one person was quicker than the other, the power's going to be different. So the person who is taking twice as long is only going to have half the power because they are doing it in double the amount of time. So on the odd occasion, you get a bit of a question like this, just for the example, to be able to test your understanding and make sure that you actually know what these equations mean, rather than just being able to remember them and do the calculations. You actually understand what these equations are for. Okay, thanks for watching my lesson on work and power. It's goodbye from Mrs. Jones, and it's goodbye from Thor.